Okay, so I guess we're all set for today's seminar. Thanks so much for coming. Today we're having Professor Kate Maguire. Kate did her PhD at the Queen University in Belfast, and afterwards went on to do postdocs in Oxford, also at the European Southern Observatory in Munich, where he actually where she had a Marie Curie fellowship. And after being again in Belfast, currently she's an associate professor at Trinity College in Dublin. We're also the beneficiary of an ERC grant, correct?
Yes. Yeah.
I will have to say all the merit. So without more details, Phil, thank you for coming and thanks for the seminar.
Thanks very much, Alex. It's great to be here. I've had a great time so far. So yeah, today I'm going to tell you about exploding stars and catastrophic collisions through the universe. So I'm an astrophysicist who does observations and some connection to theory. So I know there's some people in the audience don't do anything similar to that. So I'm going to try and start off relatively basic and give you some of the background. So we'll see how that goes. Okay, so why do we want to understand things that explode in the universe? Some of the most energetic explosions like supernovae, neutron-star mergers. So there are a number of reasons.
Okay,
I'm
not seeing the changing slides on the video. That's going to be like afterwards the meeting recording will not be fine. If you could unshare and share them, I'm really sorry for that.
Sure.
Thank you, Alex.
Yeah. Okay, great.
Thank you, and sorry for the
no problem. Okay, so yeah, I want to tell you why we want to study explosions in the universe. So one of the main reasons, or one of the reasons I'm particularly interested in, is to understand nucleosynthesis. So the origin of the elements that exist. So elements like iron, each type 1a supernova, so a particular type of supernova, produces about half a solar mass of iron in the explosion. And this is the origin of iron that we have on Earth. And then in kilonova explosions from neutron-star mergers, this is where we get a lot of the R process elements, so heavier elements like gold are produced in these explosions. So understanding how different types of events, how much of these different elements they produce, and then combining that with the rates can tell us where heavy elements come from in the universe. Then supernovae are also very important for powering feedback dynamics in galaxies because of their great explosions. They can control how galaxies evolve. I'm not going to go into any details on that in this talk. And then probably where they're most famous, let's say, is for the discovery of dark energy. So for using explosions in the universe to understand how far away type 1a supernovae are, and then we can measure distances. And this helps us understand the makeup of the universe. So we're currently in the era of precision cosmology, where we know that approximately 68% of the mass energy of the universe is in the form of dark energy. So this mysterious quantity that we don't quite know what it is, but it's consistent with the cosmological constant. And there's a lot of interest in this topic at the moment, also because of this so-called Hubble tension, differences in the Hubble measurement between the distant universe and then local measurements where supernovae are involved with Cepheid. And so there's a lot of interest in understanding or constraining the systematics in these measurements to see if this tension between the value is real. And it really comes down, so the future of supernova 1a cosmology, I think, can be boiled down into two different issues that arise that we want to try and constrain. So one is calibration, which I think is relatively boring, but very important. So really understanding like the photometric systems that we use, so how telescopes are calibrated to understand if what we're measuring with one telescope, say, is the same as we're measuring with another telescope. But perhaps more interesting, and what I'm particularly interested in, is understanding supernova 1a physics. So when we have an explosion, what's constraining the properties of the star, and how does this impact how we can use them to measure distances in the universe? So the particular type of supernova that I'm interested in particularly is type 1a supernovae. So I think you've had some talks on them before, but just to give you a brief recap, so these are really important for measuring distances in the universe. And the reason for that is you may have heard them called standard candles, but they're actually standardizable candles because we have to make corrections to their brightness to use them to measure distances in the universe. So we can, so essentially they're like a light bulb or a candle that we can put at some distance. We know how bright they are, and then that means we can measure the distance. We can tell how far away they are. And this allows us to constrain the evolution of the universe. And so we have to make 3 broad corrections to their light curves. So the first is shown here. So here you can see the uncorrected light curves of some type 1a supernovae. This is their brightness as a function of time. And so you can see they have different brightnesses, but this correlates very well with the width of the light curve. So the brighter ones have broader light curves, and the fainter ones have faster evolving light curves. And so we can make a correction for this, which makes them better standardizable candles. The second correction we can make is for the brightness and the color of the supernova. So how it appears in, say, at different wavelengths. So if we look at different wavelengths in the optical, how does it compare to bluer versus redder wavelengths? This is work that Santiago is very involved in understanding colors in type 1a supernovae. And so those are both, you can probably think that these different parameters that we make the correction for could have something to do with the physics of the explosions themselves. But really, when they're used in supernova 1a cosmology, they're empirical corrections that we use. And the third one, I would say, is the weirdest of the 3 corrections that we use. And so generally it's parameterized in a couple of different ways. But one way is that the brightness of the supernova correlates with the stellar mass of the host galaxy that it explodes in, which seems pretty unconnected. Like you have the total mass of stars in that galaxy, and that somehow impacts how bright a supernova that occurs in that galaxy is. And so it's probably, or it's very likely that it's not really the stellar mass that's impacting this or influencing this. It's something else in the physics. So maybe the age of the stars that explode, or the how many metals are in the environment that they explode in. But a correction is made for this in the precision cosmology, and it's formulated in a couple of different ways. But it does improve the measurements, and it is used. So then how do we, just briefly recapping, how do we use type 1a supernovae then? So what we do is we can measure this distance after these corrections. So we say, okay, we know how bright they are after we make the corrections. And then we can measure the recessional velocity from lines in the galaxy spectrum. We can measure the redshift, so how far away from us it is. And then if the universe was a simple coasting universe, you'd expect the supernovae, as we observe them at different distances, to fall on this line. If they fall below here, then you would say gravity is winning in the universe, and the mass of objects is pulling the universe to make it smaller. And so you'd say the expansion rate then would be decelerating. And so this is what people expected. And that this would be, so in the 90s, when they went out to make these measurements, this is what they expected to find. And if gravity was losing, then in the expansion rate of the universe, as we now know, is accelerating, we'd expect them to sit here. So this was the expected result. And then this is what was actually seen. And so this tells us there's something acting against gravity in the universe to cause the expansion rate to accelerate. And so this is called dark energy. And so we now know this makes up 68% of the mass energy of the universe.
Can I ask a question?
Yeah.
Regarding the previous slide. So you're aligning all these curves empirically.
Mm-hmm.
But how do you know that it's a nice thing that they align? But is there any theoretical reason why you should?
Yeah, so I'll describe a little bit on it. So there are reasons that, depending on so these are white dwarfs that are exploding. So related to their carbon-oxygen ratio in the star that explodes, and then this could produce different amounts of nickel in the explosion. So the nickel decays in a radioactive.
So there's strong reasons why you.
Yeah, there's strong reasons, I would say, but like the cosmology still works even though we don't know why. Yeah, so I think, yeah, there's reasons for all of them. There's also reasons for the color correction, like the brighter ones are bluer, they're perhaps hotter. So yeah, there are reasons for it, but the original measurements were empirical. Okay, and then just to show you then, finally, so this is the Nobel Prize winning data. So in 2011, the 2 teams that went out to measure these supernovae in the distant universe. And so this is their data. And so it's the residual from a universe with matter equal to 0.3. And so the key part here is that the supernovae in the distant universe were fainter than was expected. And so this tells us that the universe, or told them that the universe was accelerating. Okay, so that's just a brief recap on 1A cosmology. Are there any other questions at this point? Okay. All right, so yeah, as I said, I'm interested in the physics of the explosions. And so in the rest of the talk, I'm going to look at constraining how type 1A supernovae explodes, try and tell you a bit about what is actually exploding to make so that we can use these as distance indicators. And then in the last part, I'll talk about some of these fainter, more exotic explosions that we've been seeing in some of the sky surveys recently. Okay, yes.
I actually have another question.
Yeah.
About the color of the stars. So I wonder what you are looking at specifically. I mean, because there's one part where the color changes due to the temperature of the star, and another part where it changes due to gravitational cosmological redshift.
Oh, yes, yeah, yeah.
So are you looking at spectra really, and you see where the helium or hydrogen is in the spectrum?
So yeah, when we talk, so this is when it's all being corrected to the local rest frame. So when we compare colors between supernovae close by and at high redshift, it's already being corrected. And then it is a combination of temperature plus the features that we have. So then that depends on what the elemental abundances are in the supernova as well. So it's a combination of both.
Okay, but do you disentangle them actually? Or?
So the cosmological measurements are made with photometry, so it's binned over a certain wavelength range. So we're not resolving then particular spectral features, so they'd be over quite a broad range that we use for filters. Yeah.
Probably when something fractions that you do for the distance are the same for the D in D filter. So when you subtract, they can go out. The ones that cosmological corrections for the D
For the color.
for the so the correction you do for the D filter, but the dependence on the D filter and on the other filter are the same. And when you subtract, they can go out. When you left, you can see. Is that correct?
Yeah, so it has to be corrected for the redshift of the object,
Yeah, but
so that it's the same
correction
part of the
for-
spectrum. But yeah,
For the D, when you subtract, they are removed.
so we end up with some of the supernovae will be slightly redder and some will be slightly bluer. So there's a small part left, but it is important to include
But it's increasing.
to the
Color is
supernova. Yeah,
increasing.
yeah.
Technological part. Often
Yeah. Okay, so then yeah, on the explosion type, then the first scenario that people think, so how do you get this white dwarf to explode? And so the first scenario is that you have a white dwarf and it's accreting matter of another star that's not another white dwarf. So we call it a non-degenerate companion. This could be some type of red giant or a main sequence star like our sun. And so what will happen is the white dwarf that's here will accrete matter from the companion star. It gets close to the Chandrasekhar mass limit, which is the maximum mass that can be supported by electron degeneracy pressure. And you get a runaway thermonuclear reaction in the star and it explodes. And so the white dwarf itself is completely destroyed. So this is one kind of, I would say, the classical scenario for how a type 1A supernova occurs. So it's useful because they're all close to the Chandrasekhar mass when they explode. They may have the same mass, which explains, given small differences, why you can use them for cosmology. There's another scenario, so the double degenerate. This is where you have another white dwarf in the binary system. There's a couple of different ways where you can get this explosion. So one would be the merger by the release of gravitational waves, so they spiral in. you get some kind of explosion. I think this very specific, where you have two white dwarfs merging in this way, is probably unlikely. But there are a couple of different ways that we can look at this. So really, when we're looking at these two different scenarios, we're considering explosions that are at the Chandrasekhar mass, and this has implications for the density of the star at the time of explosion. Or you can have ones that are what we call sub-Chandrasekhar mass, so less than 1.4 solar masses. They'll still be quite close to the Chandrasekhar mass limit, but not quite at it. And so then within these, in the last decades, there have been loads of attempts or loads of different theories to try and explain how type 1a supernovae occur. And so you can have accretion from winds or from Roche-Love overflow in different ways at the Chandrasekhar mass. But then there's also loads of different models for explosions of white dwarfs that are below this Chandrasekhar mass. So you can have the mergers, which is what I showed in the video. You can actually have the direct collisions of stars if you have a triple system in a wider orbit, so you can get them directly colliding. But probably one of the most promising at the moment, or very popular in the community, is a white dwarf with a thin layer of helium on the surface. So this could be accreting either from a helium star, from a non-degenerate companion star, or it could be from a white dwarf with some helium on its surface. And so what happens here is you get the helium layer builds up from the accretion. It is detonated, but it gets to certain densities and temperatures. This explodes, and then there's a shock wave that passes into the star, and then this causes the core to also explode. And so this is a popular method at the moment. So one of the things that I'm particularly interested in looking at is how do we distinguish between these explosion scenarios? So how do we decide what's actually occurring? So as I said, I work with observations. We want to try and go out and take different observations that can try and link back to how the actual supernova explodes. And so this just shows a light curve of a supernova, so your flux, your luminosity, as a function of time. So this is the typical shape that it has. And so it's powered by the light curve of a type 1a supernova is powered by the radioactive decay of nickel-56 that's produced in the explosion. So we don't see the explosion itself, we see the radioactive powering. So that's what gives us this light curve. And so we can look at different points in the supernova light curve, and we can look for different signatures that tell us about what's going on. So one of these is at very early times. You can imagine if we have the white dwarf exploding and we have this star like the sun nearby, you could get some kind of interaction between the white dwarf, the ejecta, from the explosion interacting with this companion star. This can give an additional bump in the light curve, an additional flux. And so this is one way I'll talk a little bit more about. And then we can also look at other features, which I won't go into in much detail now. But we can look at different points in the evolution of the supernova and try and understand what's actually happening and how this can be linked back to the progenitor scenario. Okay, and then we can also, so one of the key things, and it's very popular at the moment, is to try and understand this connection that I mentioned with the host galaxy properties. So trying to understand how the connection between the supernova that explodes and, say, the stellar mass or the age of the stellar population it results from connects. So one of the issues historically with studies that were used for cosmology was that what we call the cadence of the light curve. So how long between each observation we take of the supernova was too long, or it was too low cadence, and to really understand the physics. So if you want to go out and get a big survey of type 1a supernova for cosmology, you probably only need to sample it like this. So if these are your data points, every 3 to 5 days is probably fine. But if you really want to understand the physics, you want to be looking in this kind of region. And so previous surveys weren't really probing this kind of area. They were just trying to get the observations. So as I said, if you have your exploding white dwarf and you have your companion star here, you can get some kind of interaction between the ejecta and this companion star. And so the way this manifests itself then is, if you look again at the light curve of the supernova, in the first few days after explosion, you see an additional bump in the light curve. So this is like a flux from this interaction. And so what's shown here is, so in black is if there's no companion, interactions. These are different model scenarios. The red is if you have a 2 solar mass main sequence star, blue is 6 solar mass, and then the green is a 1 solar mass red giant. And it really depends on the radius of the star. And so you can get these different signatures. But historically, it was very hard to try and get these observations. So in recent years, we've been going out to try and find this. Now, of course, theorists are, when you predict something like this, and a couple of these bumps, as we call them, have been found, theorists have come up with other ways to try and explain these using their preferred model. So one way is how you mix. So like where the nickel is produced as a function of radius from the center of the star and can impact what the early light curve looks like. In this, as I said, this popular helium shell detonation, you can imagine if when the helium shell detonates, this could produce an initial bump, and then you see the main explosion of the core. Or you could have interaction with circumstellar material. So if you had a previous mass loss from your star, you can imagine a kind of messy environment that the supernova is then exploding into, and this could produce a signature. And so people have gone out and tried to find these flux excesses. So here again, more light curves. So the dashed line here is kind of a model without flux excess. And then with this additional shock interaction, the data or the points, you can see this model with shock interaction fits the light curves differently. And so these are just different filters that's going from the ultraviolet to the infrared. And so you can see you need this additional component. And so the issue is it's kind of hard to tell what the different scenarios I showed on the previous slide. It's hard to link it back just when you have photometry alone. And we do have some very extreme cases where here, so in very early times, you can see that it's not even just a smooth rise, it's actually in the UV filters, which are these blue and purple. It's really bright at early times, and then it gets fainter, and then it creases again. This is a really strong interaction signature at early times. So we've seen this in a handful of objects. So what we wanted to do recently was to go out and get a larger sample of these.
But so this is some of these for companions?
So for these particular models, yes. So say here for this shock, it's some companion interaction. So it's typically 3 times the radius of the star, where it was secreting by rotational overflow.
And so are there systems where you're gonna have to compare them?
Yeah. So would be so the models are based on real binary systems, involving white dwarfs and non-degenerate companion stars. Yeah. So I think that's relatively well understood. So we wanted to go out and try and, or many people wanted to go out and try and get observations. These are some of the telescopes that try throughout the world that try and do these studies, and they're based in Hawaii, Chile, in the Canary Islands, and so I'm particularly involved in the Zwicky Transient Facility. So it's based in Palomar in California, and so it's 47 square degree field of view, and it's doing an optical survey of the night sky over a large portion of the night sky. And so this is just a video showing us some of the light curves that we obtained since the 2 optical filters in the G band and the R band. And this just shows some of the light curves that we've been obtaining. This was an initial sample of 130 events. And so what we want to try and do is to go out and look for these flux excesses in the early light curves. It's not all of the objects, as you'll see, they don't all have very early data, but a lot of them do. So we say like the explosion is marked here, and then we have data in this early part of the light curve, so we can try and constrain what's going on. And so then this is work done by a PhD student of mine, Maxine Deckers. And so what we're looking at here is the absolute magnitude of supernova again. So again, the light curves, and this is for different supernovae are shown here. So I think the key thing you want to take away from this is that this would be a normal type 1a supernova. So say this blue line, but we're seeing these objects that show an excess at early times. So what we've done here is we've done a systematic survey. So previously people were going out and maybe getting early observations for one event, and then we have to say, okay, there's something there. But we wanted to check consistently in a larger sample. And so we've done that for the 130 objects now. And we find approximately 20% of the normal 1As have these bump in the early light curve. And so we can try and, based on the properties, try and constrain which of the progenitor scenarios is the most likely. So this is showing the color. So the two optical filters, so a bluer band and a redder band, 3 days post-explosion here on the light curve. And then as a function of how long this flux excess lasts, so where does it kind of join the normal rise of a type 1A supernova. And so the points are some of the objects we found, and then you've got these two models of the companion interaction and then a nickel clump, two different models. And you can see that you can't really tell between them in this, unfortunately. We can't, so we found the bumps, we can say they're present in 20% of the objects, but based on the observations we have so far, it's quite hard to link back. What we can say is that 4 of them are inconsistent with interaction with circumstellar material. So these ones over here, the circumstellar interaction tends to have a lot shorter time scale from the models. And they're also all inconsistent with the double detonation, so the helium shell detonation. But for these 20%.
So the nickel clump is not related to the double detonation. That's just the distribution of nickel that it.
Yeah, it's just the distribution of nickel and the ejecta. Yeah.
Okay.
Yes.
Sorry. You assume that the line to the right is the correct one.
And so we see
Yeah.
this.
Why you don't move it to the left and then all the others will be normal?
So because we have, it's a good question. So we have this particular object, you can't really see it underneath, but 11Fe, one of the nearest by type 1A supernovae. And so we know that this was an object, a very well studied object that rose in that sense. So compared to that object, there's an excess of the early times.
The supernovae use, they are the distance such that it's totally confirmed? Or
Yeah. Yes, yeah, they all have spectroscopic redshifts, yeah.
So you're thinking 20%, do you know how many of them have been damaged?
No,
This is-
no. So we don't, so these systems are so faint, it's not, even if there was imaging of that particular area of sky before, we can't see anything in it to start with. So we have no idea. We can only study the supernova.
The other 80% look like 11Fe.
And so there is some variation, like there's a decent variation in the rise times, but yeah, kind of like a smooth rise that's approximately consistent. Yeah. Okay, so yeah, I think so what I want you to take from that is about 20% of them show these excesses. So I showed you all these different ways that you can study type 1A supernovae. The other one that I want to mention is this late time nucleosynthesis. So this can tell us about what ratios of iron and nickel are produced in the explosions. And so there's different predictions depending on whether you have an explosion at the Chandrasekhar mass or below the Chandrasekhar mass. So if it's approximately 1.4 times the mass of the sun, you end up with something that has a higher central density. And so what happens is you get more electron capture because of this higher density. And so you end up with more neutron-rich material. And so this means you have more stable materials, so more stable nickel-58 and iron-54. Whereas alternatively, if you have a sub-Chandrasekhar mass explosion, it has a lower central density, but less electron capture, and you end up with more radioactive nickel. So then trying to understand the ratio of the stable material to the radioactive material can tell us something about the mass of the white dwarf at the time of explosion. And so if we want to try and look at this, we want to go to very late times in the supernova interaction. So at early times, when the supernovas just exploded, the ejecta are optically thick, and so we can't see into the core. So any measurements we make, we can't see like the total mass of the material that's been produced. But as it expands over time, it becomes optically thin. And so if we look at maybe a year after explosion, we can see the total mass of the ejecta. And so this is why we want to look at these kind of epochs in here. It's like 360 days. And so these are spectra in the optical, so from about 4,000 angstroms out to 21,000 angstroms. And so the spectra are dominated by forbidden iron lines. The key area that we want to look at is this nickel, the nickel line here. So the reason for this is 56 radioactive nickel is produced in the explosion. As I told you, that's what powers the whole light curve. But it has a half-life of about 6.1 days. And then the cobalt decays to cobalt, and then the cobalt decays in 7 days to iron. And so if you look at about a year after explosion, all the radioactive nickel that was produced in the explosion should have decayed away. And so if you see any material, then it should be stable material. So then we can link that back to the progenitor scenario. And so this is what we looked at. We looked at this ratio of the nickel over iron. So I won't explain this plot in too much detail, but what I just want to say is that these are different model predictions. And so I'm going to put the data on the plot now in a second. But if the data points lie in this region, then it's prediction for the Chandrasekhar mass explosions. And if they have lower values of nickel, for the subchandras here. And so when we did this for a small handful of objects, error bars are large, and so it's hard to definitively tell between it. But this type of region is more consistent with Chandrasekhar mass explosions, so some kind of non-degenerate companion star. And if you want to try and explain it with subchandra models, which some people do, what you need to do is you need to increase the white dwarf. The metallicity of the white dwarf affects some of the processes that produce the rate that influence the ratio of the stable to radioactive material. So this was in 2018, and then a more recent paper in 2020 I went out to do the same measurements but in a lot larger sample. So here again, so this is the nickel over iron ratio, and then you have the shaded region shows the sub-Chandrasekhar mass explosions, and then these are the Chandrasekhar mass. And so what they found from I think better calculation is that the peak of the distribution, the probability distribution, was for sub-Chandrasekhar explosions. And there's some caveats that I won't go into, but it seemed more likely. And so then what's the conclusion then of these two different probes of the progenitors of type 1a supernovae? So as I said, there's the early bumps that we think are probably more consistent with some kind of interaction with the non-degenerate companion star. But then we have nickel over iron ratios seem to suggest that most of them are subchandra explosions. And so I think most people in the community now believe that both scenarios are probably likely. So maybe it's these 20% of type 1a supernovae that come from the single degenerate explosions at the Chandrasekhar mass limit. And then we have 80% that are from another. So this can be a little bit difficult then if you want to use these for cosmology. People can start to worry that this influence, if you have two different ways of producing a type 1a supernova, is this going to introduce biases in your cosmology? I don't think it's going to impact dark energy, but it may have subtle effects, and so this is why people are trying to understand this in more detail. Okay, so then in the last bit of my talk, I said I wanted to talk about some of these exotic transients that we've seen in recent times. So I've shown you a lot of light curves of type 1a supernovae. They have this kind of shape, but also in these high cadence sky surveys that we have now, we're seeing events that evolve a lot faster and fainter than normal events. And they may have some quite exotic origins. So one scenario is some kind of tidal disruption event by a intermediate mass black hole is one of the predictions. So there are models, these intermediate mass black holes, so between the mass of stellar mass black holes and our supermassive black holes. People think the intermediate mass ones must exist, but they're very, very hard to find. And so there are predictions that you could get the explosion of a white dwarf in this scenario. And so if we could see these, this would be good proof of intermediate mass black holes. There's also models that suggest you could have just the helium shell detonation on the surface of the white dwarf. Maybe it's not quite energetic enough to trigger the core detonation. And so you just have a much smaller little blip. And then there are also exotic models of white-dwarf neutron-star mergers that can also produce quite faint and fast events. This is another way of looking at the diversity of type 1a supernovae. So the gray ones here in the middle of the plot, so these are the ones we use for cosmology. And this is showing their brightness, fainter down here, and then faster evolving here. These are ones from the Zwicky Transient Facility. And what you can see is there's a lot of events. So each of these points is a supernova that we have discovered. And so it parameterizes brightness and then how fast it evolves. And so we're seeing this huge diversity. So things down at -12 magnitude. So normal type 1a has about a magnitude of -19 or something like that. These are orders of magnitude fainter. And we still think they're associated with a white dwarf. They must have a different explosion scenario. Yeah, so the normal ones sit here. These blue ones, we found a good few of these objects. They're called 1A X's. So people didn't know what they were. They just put an X after the 1A. And so people think that the weak explosions of Chandrasekhar mass, white dwarfs, they're very interesting because they haven't completely destroyed the star. There's some kind of bound remnant left at the end, so they're quite weak. And so people then can go out and try and take deep images to try and find that stellar remnant that's left behind. And the other object that or other class of objects that I'll just mention briefly are the calcium strong transients. These show very strong calcium in their spectra, not surprisingly based on their name. But they have pretty interesting locations. So each of these is so in the crosshairs here is the position that this transient was discovered. And so you can see they're quite offset from the centers of their galaxy. So typically the supernovae would follow the light of the galaxies. And these are quite offset locations. They're interesting because they're faint, they're hard to find. But when you make corrections for like the fact that they're harder to find, the rates of these objects are actually quite high. So like the intrinsic rate, how often they explode is quite high. And so it could be as high as basically the normal type 1a supernova rate. And so they're also very useful because there's this issue in the intra-cluster medium where there's an overabundance of calcium compared to what is predicted from normal type 1a supernovae and normal explosions of massive stars. So that's what's shown here. So this is the abundance ratio of different elements. And this is a function of atomic number. The black points are the data that's been obtained. And then the blue is for your core collapse supernovae and your red is for your 1As. And so when you combine these, you get the black one. And you can see that calcium sits way above the predictions. Don't have this additional contribution. But if you include, as this sits above here, but then if you include a contribution from calcium strong or calcium rich transient to get much better match to the data. And so this suggests that the rates we're getting, that these are occurring at approximately the same rate as type 1a supernovae, is probably true. And so one of the key things is to try and understand what these explosions are. And so we don't know. Okay, so how are we going to make progress then in the next decade in this? And so this is just showing you an idea. So this is the total number of supernovae discovered as a function of year. And so first extragalactic supernova, and then people started doing surveys by eye, looking at photographic plates, to try and find what they considered new stars that had appeared. But it's really been in the last couple of decades. It's when the acceleration universe was discovered in the late 90s. It's really exploded in the number of events that we've found. And so the Vera Rubin Observatory, the LSST survey, is going to start in the next couple of years. And it's going to find greater than 10 times more supernovae than the best current surveys. The issue with it is that what we really want to have to understand the supernovae is a spectrum. So we want to be able to break down the light into the different wavelengths, really understand what's going on. And that's essentially impossible. Normally we take a spectrum of like a supernova. So we point a telescope for an hour at a particular part of the sky, and that's just not feasible with the numbers that we're going to be discovering. So one way around this is to use what we call a multi-object spectroscopic telescope. It's called Foremost. And so what you have here is you have nearly 2,500 fibers, and so each of these fibers can take a spectrum. So instead of just taking an image, it can actually break down the light, and so it's quite a subtle little movie. But you can see the little fiber arms here. And so what we do is we can tell the telescope where we want to point, and then they can move the fibers in that field of view to make a spectrum. And so we're going to do this with a survey called TIDES, the time domain extragalactic survey. And the idea here is that wherever Foremost points, and there'll be live transients, and then we can also study their galaxies as well. So I won't go into too much detail on this, but there's three main science goals that we have. The first is to try and understand all these exotic explosions. Then we obviously want to do a really good study of dark energy with type 1a supernovae. And then there's also another part of the survey that's looking at AGN physics and using them for cosmology from reverberation mapping. So just to give you a bit of a scale of how many objects we're going to have. I'm going to play the movie now in a second. This is going to show you the LSST survey, so an optical survey that's just tiling out the sky with images. And so it'll find the supernovae. And so this is just clocking up in day, the different pointings. And then the red points are where this Foremost telescope is going to overlap with it. And so we're going to find approximately, we're going to be able to target approximately 15 type 1a supernovas to get a spectrum of 15 objects in each pointing of the Foremost field. And so the kind of numbers then we're going to find.
Which is fully dedicated to LSST.
No, not at all. No, just this survey. So they also want to do galaxies. So one of the main surveys is looking at galaxies at different redshifts. Yeah. So it's actually quite a small component. So yeah, there's the 2,400 fibers, and only 15 of them per field are going to be transients.
But constantly during the full night, you have 15 available?
15, yeah, so maybe 10 pointings a night. It's like 150 spectra a night. Yeah. So over the full survey then, so this is the number of objects that we'll find in different categories as a function of redshift. So the numbers just depend on the signal to noise of the spectra. We're approximately looking here, so if you average these like 20,000 type 1a spectra over the Foremost survey, and then we'll find smaller amounts of other types of events. But the key thing is we're going to be getting spectra of like an order of magnitude more than was previously possible. And then this will also allow us to probe down to the kind of regime of kilonovae, which are produced by neutron-star mergers, and then hopefully into this unknown regime of very short timescale transients to see what might exist. And so, as I said, yeah, the spectra are key then, and because we're going to be getting so much or so many of them, we want to do some kind of spectral emulation to try and compare it to models. You can't really be modeling an individual event, we'll just have so many. And so this is work that we're looking at currently. Okay, so then in the last just a couple of minutes, so related to this, I just want to mention a little bit about the exciting area of gravitational wave astrophysics that's going to be starting again in the next month or so. Neutron-star mergers were very exciting when we found the first kilonova with a gravitational wave counterpart in 2017. But we're particularly interested in these from a nucleosynthesis point of view, so trying to understand what is the origin of our process elements and so heavier elements in the universe. So originally people thought it must be core collapse supernovae, so very neutron rich, and we have a lot of neutrons in a core collapse supernova, so the collapse of a massive star, or they could be formed in neutron-star mergers. And so we're looking at this kind of range. So this is abundances as a function of atomic mass number. So these are light R process elements and your heavy R process elements. And so we want to try and see are neutron-star mergers the origin of these. And so this was possible in 2017 with the discovery with the LIGO Virgo detectors, the gravitational wave detectors, and found this event, which is called 1708-17. So the gravitational wave detectors found it. They told us what area of sky it was potentially located in, or was located in. And this is the map of the sky. And so the LIGO detector is shown in green here, and then you have the dark green, the other Virgo detector. And then there were detections with Fermi and integral high energy detections. And so we were able to localize, or people were able to localize very quickly the location of this particular event. And so that's what's shown here. This is the host galaxy of this event. This is an old image before it exploded, or before the merger. And then you can see the little point just there, where the explosion was seen. So it was a fantastic opportunity to go out and study this kilonova or neutron-star merger in great detail. We took excellent photometric data, loads of spectra, and one of the key reasons was to try and constrain the nucleosynthesis. And so this was some initial modeling that was done. So there were tentative detections of cesium and tellurium in the spectrum. So the red, the black is the data, and then the red shows this model that fits these features better if these R process elements are included. More recent modeling has shown that there's also strontium, so another R process element. And so what we want to do now is to try and understand, can kilonovae explain all of the R process nucleosynthesis? So we have one event with the gravitational wave counterpart, and so we want to try and study this in more detail. So I'm involved in the N-grade collaborations, the electromagnetic counterparts of gravitational wave source, very large telescope. And so we want to, when a new event is discovered, we want to try and take photometry and spectroscopy and polarimetry and understand the host. And so it's particularly timely now because the next gravitational wave runs are starting, the official run starts next month, so I think 24th or 25th of May. So they start engineering in the next week or so, an engineering run of these telescopes, and then this will run for 18 months. So we're hopeful that we're going to find another kilonova, and then the key, so when they release the detection, is to go out and try and get the observations very quickly. Okay, so then to summarize, I hope I haven't put you off too much that type 1a supernovae are really useful for cosmology, even if we don't completely understand how they explode, or even the fact that there's likely a contribution from multiple progenitor channels. I think one of the keys is trying to get spectra now of the observations. We can't just rely on the photometry, and so foremost would be really great for this. And then I think the combination of studying the kilonovae along with other types of supernovae can really give us a handle on the heavy element nucleosynthesis in the universe. Okay, thanks very much. Do you have any questions?
Thanks very much. Very nicely timed. For this.
Thanks for the talk. The shallow sector mass triggers a dynamical instability, so the star should collapse. Now, I always have the question about if this explosion has anything to do with the shallow sector mass. And you find in the books sometimes, in the papers, sometimes they say yes, sometimes they say no, in a sense. But there are stars that explode at the shallow sector mass, so it should be connected to the explosion of the shallow sector mass. But now I see that there are other stars that explode at sub-shallow sector mass. That the explosion is not connected with.
No, and so honestly, even in the ones that we technically call Chandrasekhar mass explosions, it's really because they've reached a certain density and temperature that the thermonuclear explosion is triggered. It's not, I would say nearly it's coincidental that it's close to the Chandrasekhar mass. Yeah, I think you're right. Yeah. Well, maybe not coincidental, but well, yeah, I guess, yeah. Because so it's really the burning of the carbon and oxygen in the white dwarf, and that could occur if it occurred at a temperature that was obtained at lower mass, then that's when it would explode.
So, even the fiber have some type of supernova are more luminous and some other. Do you think that can be explained by the connection, I mean, the line of view we are watching the explosion? I mean, assuming the explosions have some asymmetry, maybe the direction here watching that explosion may come to type of supernova.
Yeah, no, I think you're right. So when I showed all those bumps in the 20% of objects, it's probably likely that the real intrinsic, well, so that is the intrinsic rate, but there's a correction, yeah, for the viewing angle. So you can imagine if the supernova explodes and that companion star is on the other side, you're not going to see that additional bump in the light curve. And so it does depend on the direction that you're viewing it from. Yeah. So yeah, it is an additional complication.
Then we are more, we are more comparable with the beginning of the light medium that may be
Yeah, you're right. It does kind of get blurred out more with time. Yeah. The issue is like you'd really want very early polarimetric data. So very early polarimetry, but it's hard to do that. So the objects need to be very bright. And so typically they're quite faint, but there are some people trying to do that. Yeah.
Okay, so what exactly is the impact of the systematics on the ability to resolve the tension, the Hubble tension?
So some people say that it still won't be enough, even if we've underestimated the systematics. I probably think there perhaps are unknown systematics.
Oh, yeah.
So, but like, they do really good calculations, like 100 different things, and they calculate what would be the systematical effect of changing each of those. But there are likely ones that, aren't considered. I think as time goes on, and there have been very careful studies, I think it probably is real. And then you're invoking different, theories. But I think probably the significance may go down, I think, with bigger studies. So for the Hubble tension, like the number of supernovae that are used in those in the calibrator samples, so the combined galaxies that have a supernova and say a Cepheid measurement, they're relatively small samples, like they're tens of objects.
But this is relevant for
Yeah.
you, though, because you might tell readers and not okay, right? We understand this.
Yeah.
But again, it's not going to have an impact on the reflex.
So I don't think it'll massively change the measurements of dark energy. I think it has a much greater impact on the Hubble tension, just because the samples. So for the cosmology, for the dark energy, you're looking at thousands of supernovae, but the ones that are used in the Hubble measurements in the local universe are like tens of objects. So like if there's something weird going on in some of those, particularly with Cepheids, like so you see them more in certain galaxy types, and so then if there's some galaxy dependence, it matters a lot more. Yeah.
It's for to understand the nature of that energy. The question of the control of the systematic.
Yeah, I think now, so it's only.
There is dark energy. Let's
Yes,
assume
yeah.
we know. But what is it that the question of state? That is systematic.
Yeah, so I think it's probably like it's only really now that we're getting into the statistical uncertainty is now smaller than the systematic uncertainties in it. And so it will start to matter more, but probably a lot of it is still in the calibration. But I think, with like future surveys like LSST, we could get to the point that, where if we want to understand the equation of state, we have to understand these systematics.
It's cosmological. You don't need to worry.
Just to make sure.
Yeah, just make sure.
Yeah, I was wondering in the when you were showing the different models, CSM and the nickel mixing, why is CSM so narrow in terms of days? I think it was, right?
That is because in general the models assume that the extent of the CSM is quite small in the models.
So can you just like
You could, yeah. But I think the predictions of, like, say, if you had a nova eruption or something like that, it would be quite narrow. Because it's just based on that. But yeah, I think you probably could change it a bit.
And in that same plot, you showed the nickel mixing, but you didn't show the double detonation prediction.
Yeah, I think models have come out now, but I don't think they were there at the time. Yeah, we put everything that we could onto the plot, but we didn't have it yet.
We've got 1 more minute, one more chance for a question.
It's regarding the last question of can or unprocessed elements can be explained. What would be the best one? Like some European abundance, some studies say that they need a quantity control. So if you have to bet today.
I think it's never just one thing, isn't it not? So I'd probably bet for both, yeah. But I think the rate, just because we have there's a few kilonova candidates that don't have the gravitational wave detections as well, but not detailed observations. But we still don't know, like, what's the diversity in the kilonovae, what's their rate, like how do we scale it up from the few events we have? So yeah, it's very hard to tell, but I'd probably bet on both, yeah.
That's a safe bet.
Yeah, I think so. I could be right either way.
Unless there's a very last short question, then I suggest we thank our speaker.
Okay.
If you enjoyed the video, like and subscribe.